Thank you very much for organizing the seminar for me. So today I would like to talk about slow pseudotachylites, which might sense like a uttermost nonsense in the first place, but I'll try to convince you that it actually makes sense. And I've been working on this it appeared from my PhD thesis work, and we joined in with Martin Drury from University of Utrecht and Christian De Capitani from Basel to try to solve this problem. So today I'll talk how do we get actually to this kind of pseudotachylites that have a very typical microstructure that are observed in pseudotachylites, which are flow structures, injection veins, some bubbles, and I'll show you what is the material that this thing evolves from, which would be those slip zones, and I'll try to put some implications of our observation. So first of all, just a short introduction. What is a pseudotachylite at all? So a pseudotachylite, it's a very fine-grained aphanitic rock that was first described by Shand 1916 in the Vredefort impact crater. So here we have an example of a beautiful, huge pseudotachylite, which is this black material, which is very fine-grained, and it's very hard to see in the field what is it really consisting of. Shand hypothesized that this must have formed in situ by melting of the granite by some large shearing or gas fluxing, which is a interpretation that's favored until today. Then in 1975, Rick Simpson wrote his seminal paper, and that was about the generation of pseudotachylite by ancient seismic faulting. So those are these kind of pseudotachylites that he described in the Herbite's thrust, and they are found along faults. They have some injection veins, are more or less planar, thick, continuous, discontinuous, and they've been termed tectonic pseudotachylites. Because they are so fine-grained, it's very hard to see what is really the physical process behind this generation of the pseudotachylites. So there was a long-standing controversy between how do those pseudotachylites originate at all. And Weng and Weiss and Weng, they actually pointed out that previous studies failed to confirm the presence of glass in any pseudotachylite vein in the 80s. And they were arguing that extreme comminution can actually form such small grain sizes that it appears glassy on the outcrop scale. And it was argued for a long time based on field evidence whether the pseudotachylites really formed through frictional melting or whether they are a result of extreme comminution. This discussion was partly ended by the work of Spray, who actually demonstrated in a frictional welding machine that high velocity slip on a surface can produce a rock that's actually molten and that has many aspects of a typical pseudotachylites. And subsequently Shimamoto designed a high velocity friction apparatus where they can produce frictional melt, and where you can also measure the shear stress and get some technical data or mechanical data on what the pseudotachylites actually do to the faults. Then there is another theory how the pseudotachylites form, which comes from PGP here, and that's the self-localized thermal runaway theory, which was introduced by Andersen and John. And the argument was, if I got it right, that the brittle failure is unlikely at high confining pressures. So if we observe some pseudotachylites in the mantle or in the lowermost crust, it is likely that they form through extreme strain localization. However, current consensus today is that the pseudotachylites are the only unequivocal evidence for ancient earthquakes. This implies that they form at fast slip velocities, higher than 1 meter per second, which is a typical seismic speed. They form within seconds, so it's basically an adiabatic process. If an earthquake occurs, also a stress drop is observed that radiates seismic waves. And now this is more discussed, but it's very commonly assumed that the pseudotachylites lubricate the fault, can reach very high temperatures, because we observe the melting of quartz, for example, which in the matter of seconds should be a disequilibrium process. and they can be also used to infer earthquake source parameters. Now I would like to make a step back and just shortly show you how we actually got to make something that shares all the characteristics of a pseudotachylite, and that was that we were interested in the brittle plastic transition in granitoid cataclasites. So here on this diagram to the left, that's a classical diagram that shows the differential stress against the pressure. And here we have three lines. The first line is the Bayerle's rule, which states that, which actually describes the differential stress needed to slide a pre-existing fracture. The next line here is the Goetze's criterion, which is just an experimental rule of thumb that states that if the differential stress is equal or lower than the confining pressure, plastic deformation processes are favored. And the last black curve is the fracture envelope, where we have here some von Mises yield, and at some point the rocks reach their maximal compressive strength and reach the von Mises yield criterion. So based on this diagram we can define two transitions. The first one would be the point where the Bayerle's rule intersects the fracture envelope, the so-called brittle ductile transition, because from this point onwards the differential stress needed to slide a pre-existing fracture is actually higher than the rock strength surrounding this fracture, which leads to pervasive comminution of rocks and forms thicker cataclasites. And if we increase the pressure, we get to the point where the Goetze's criterion intersects the fracture envelope, and that's the so-called brittle plastic transition, where crystal plastic processes start to dominate. The main difference between frictional deformation is that it's pressure dependent and strain rate and temperature independent, more or less, whereas plastic deformation is very strongly strain rate and temperature dependent. So based on these ideas, there are the rheological profiles of the lithosphere constructed, which actually show that the uppermost part of the crust should be controlled by frictional sliding along pre-existing blocks, pre-existing fractures. Sorry, and then from the point 1, which would correspond to the brittle ductile transition, the strength of the rocks is controlled by the fracture strength, until the point 2, which roughly corresponds to the brittle plastic transition, where the rocks start deforming according to some flow law. Here we have to point out that into the depth there are many parameters that go in, like the geothermal gradient. It's plotted for a single strain rate, so this brittle to plastic transition might migrate upwards and downwards based on the current conditions, typically strain rate, which is not constant in nature. Our experimental setup is that we put crushed Versaska gneiss with a grain size smaller than 200 microns, with 0.2 weight% water added in between two pre-cut alumina forcing blocks. The Versaska gneiss is just an analog for granitoid rocks. It has a typical granitoid composition, around 35% quartz, 30 K-feldspar, 25 plage, and around 6% of micas. We deform this at 300 to 600 degrees C, at the confining pressures from 300 to 1500 MPa, with most of the experiments done around 500 MPa. We deform it in a solid medium deformation apparatus, and we use potassium iodide as a weak confining salt, where the strength of the potassium iodide cannot be measured, so we can neglect its influence on the sample strength. Now, the strain rates that we induce are 10 to the minus 3 down to 10 to the minus 5 per second, which corresponds to a slip velocity of 10 to the minus 6 down to 10 to the minus 8 meters per second. So our slip velocities that we induce, that are physically bounded by the speed by which we drive the piston down to the sample, are up to 8 orders of magnitude slower. So here I would like to point out that the strain rate is actually, shear strain rate is defined as a slip velocity divided by the thickness of the deforming zone. So we can, the slip velocity is constant, is controlled by the deformation machine. It cannot physically, no particle within this zone can move faster than the walls of the forcing blocks themselves. However, the strain rate might vary by many orders of magnitude depending on the thickness of the deforming layer. Now if we have a short look on the mechanical data, then those would be the results from the experiments at 500 MPa. We see three strain rates, 10 to the minus 3, 10 to the minus 4, and 10 to the minus 5. And we see a clear temperature dependence, where the 600 degrees C experiments are always the weakest. Then the 500 and 400 degrees C experiments, oddly enough, seem to be very similarly strong. And the 300 degrees C experiments are always the strongest. There's also a slight strain rate dependence, which is mostly pronounced by the high temperature samples. One thing that I would like to point out is that at 10 to the minus 3, which are the fastest strain rate that we deform, at 300 degrees C, shortly after reaching the peak strength, the rocks fracture. And we can see this clearly in the chart record, where there's an abrupt stress drop, a large increase in the displacement, and an audible crack. This never happens at 10 to the minus 4 or 10 to the minus 5, where the rocks just reach their peak strength and slightly weaken and continue deforming up to a gamma of 4. Yes?
The strain rates you put there is divided by the total thickness of
By the, yeah, those would be bulk strain rates. This is divided by the total thickness. Thank you. Sorry, I didn't specify this. So now if we have a look, to summarize this, we see that even at those fast strain rates, we see at those temperatures already a temperature dependence, which is a feature that's classical for some viscous or plastic deformation. If we now have a look on the influence of confining pressure, then we can see that those are experiments deformed at different confining pressures from 300 MPa to 1500 MPa at a bulk shear strain rate of 10 to the minus 4 per second at 300 degrees C. And we can see that the peak strength, the difference between the peak strength at 300 and 500 degrees C is 290 MPa roughly, and the higher the confining pressure gets, the smaller this difference gets. So if we plot this kind of data into the more space, then we can see that the experiments somewhere between 500 MPa and 1000 MPa confining pressure, there is a change in slope of the fracture envelope, where we come to a nearly a normal stress independent strength, which would correspond to the maximal compressive strength of the rocks. Now I will focus further in this talk only on the 300 degrees C experiments, where we have so far the best evidence for the pseudotachylites. I don't want to say now that there are no pseudotachylites in the other experiments, because it takes a lot of looking and searching to find them, but I can for sure say that at 300 degrees C and 500 MPa we observe pseudotachylites in all these three bulk strain rates, and only at 10 to the minus 3 we observe a fracture. So at 10 to the minus 4 there is no abrupt stress drop. What we observe though is that the displacement rate, this would be very highly stretched, so this is 10 to the minus 5 millimeters per second, so 10 to the minus 8 meters per second, goes from 1 to roughly 2, so we have here a factor of 1 in this black curve, and we can see that the displacement rate increases by about 20% when the sample weakens. This is corrected for the machine stiffness, which is actually amplifying a little bit this peak, but we can also detect it in the uncorrected data. The shear stresses sustained by those rocks are very high, around 1400 MPa. As I said, we can see here the pseudotachylites. So I will just talk about the microstructural evolution to show how do we get to these pseudotachylites. So first, the starting material was produced at a run when we just pumped it up to the experimental condition, but we didn't apply any differential stress. So this would correspond to this point on the stress strain curves. curve, and if we look in the middle of the shear zone, those would be the forcing blocks. So the sigma 1 is at 45 degrees to the pictures. We can see just a fractured cataclysite. At the end of compaction, which comes around a gamma of 1.5, you can see that this zone is pervasively cross-cut by closely spaced riedel fractures that offset the individual grains and produce a lot of fine-grained material. So if we look a little bit closer, we can here see the pervasive riedel shears that actually in between of those riedel shears we can see some larger survivor grains that can be well identified on a given magnification. They have usually an orientation which is antithetic to the induced sense of shear, which would be here right, top to the right, and those survivor grains are larger and survive in between the riedel shears, and we can also see this so-called fragmented mantles, how we call them, which is extremely finely comminuted material. All this together has a synthetic orientation with the induced sense of shear, and we call those aggregates of one phase that are delimited by face-to-face contact. So we can quantify actually this to see what how the individual minerals fracture, and we can see that this would be the survivor grains to volume of the aggregates ratio. So if we would have a grain that is formed just of a survivor grain, then we would have 100%, whereas if we would have an aggregate that's formed just out of this extremely fine-grained material, we would have a VS2 over VA ratio at 0. And we can detect two distinct trends in comminution. So quartz seems to always have more survivor grains than feldspar at a given shear strain. So this indicates that quartz is the stronger phase under these conditions, and feldspars fracture much more efficiently, probably due to their perfect cleavage. If we have a look into this extremely fine-grained material at the highest possible magnification, it's in our field emission SEM, and we can see the scale bar would be 500 nanometers, a lot of material that has the grain size on the order of 50 to 100 nanometers. So to sum this up, at the low strain we compact the rock and form a lot of closely spaced riedel fractures, and we form ourselves a cataclysite basically in the rig. Now at peak strength we can observe that those riedel shears that have been very prominent at the lower strains are actually not very well visible anymore, and we can see through-going so-called slip zones of intense deformation. So this they are very well traceable in cathodoluminescence pictures. So this would be a SEM cathodoluminescence, and here we can see that it's the same areas here taken in the backscattered electron pictures, and we can see that between this biotite, which is here in the backscatter very bright, here very dark, there is a zone of intensely shining material, which is actually feldspar material over here, and it connects to another mica. So those slip zones, they form through-going anastomosing layers that use mostly feldspar and are often associated with the presence of micas. However, the micas don't form a through-going layer in them. We can also see that within those slip zones, very often extension fractures that are associated with the putting of the experiment back to the room conditions that are associated. So, yeah, sorry, I have to say this again. I lost myself a bit. Basically, once we end the experiment, we have to take it out from 500 MPa confining pressure to room pressure again, and this leads to the extension of the zone. And the material stores some elastic deformation and some permanent deformation. So if we have a material that is permanently deformed, it can't relax elastically as efficiently as a material that surrounds it and has a larger elastic component, which will tear this permanently deformed material apart. If we have a closer look into this zone where we see that there's the most deformation going on, it has this shiny cathodoluminescent signal, then we can actually see that it's formed, it has a melanitic texture, or it looks like a myelinite, and it forms out of this K-feldspar grain that here we can resolve still some porosity, some grains are present, and here this would be the very highly shiny material where we cannot resolve any porosity, where the unloading cracks concentrate again, and which is impossible really to resolve if there are some grains or not, or what is the nature of this material. This would be another example of this. This is the fine-grained fragmented mantle, and here we have zones of this amorphous material, which we interpret that this material is actually deforming in a viscous way and is responsible for the observed temperature dependence of the deformation. If we have a look in the TEM on this, then we can see that it's formed of, this would be a TEM bright field image. Here the scale bar is 500 nanometers. So the black dots are actually crystals that are oriented in a way that they diffract, and there's a lot of crystals that have the grain size on the order of 10 nanometers. This would be the K-feldspar. We don't see any white seams that would indicate any porosity, so it's basically a zero porosity aggregate of fine-grained crystals that are embedded in this grayish matrix, which is either amorphous or crystals that are not diffracting at this orientation. And in the contact here, we see the quartz layer, where we can see those white bands, which are porosity, and the overall size of the fragments is higher, which again accompanies the observation that we made on a much larger scale, that quartz is the stronger material and fractures less. If we have a look on the diffraction pattern of this KFS material, we can see just very diffuse rings, so there's no real crystalline structure. Now just to make a point here, basically this material is on the grain size of 10 nanometers, so it fulfills the criterion to be called a nanomaterial. And the nanomaterials have actually many interesting features, because they are surface-dominated materials. So the atoms that are constituting the surface are way more abundant than the atoms that constitute the mass. And this is very well studied in the semiconductor industry. And there is seen the so-called melting point depression, which actually is a thing that's rather unintuitive, but from a certain grain size, which is on the order of nanometers, the melting point, the melting temperature starts to scale with the grain size of the individual fragments. So to see here, this Tm would be the melting size of a particle of a size d. The TMB would be the bulk melting temperature, and it scales, there's 1 minus C, which is a materials constant for covalently bond particles, again divided by D, either to the square or not. What's important here in this is that simply once we get to small particle sizes, the melting point starts being grain size dependent. And there's data, for example, on gold nanoparticles, which melt around 700 degrees C below the bulk melting temperatures if they are around 2.5 nanometers big. I didn't find any data on rocks like this, but there's quite some data on aluminium and silica and all the things that are used for the semiconductor industry. Yeah, whatever. Yeah. Well, that's they have some limits where they can study it. So I think the 2.5 nanometer large nanoparticles are the smallest that they can even produce, right? Or then it's the question, what is a particle at all? What is a grain size, right? And if we get to these small sizes. So to sum this up, at the peak strength, we observe the development of through-going slip zones that are formed of this partly amorphous material with extremely fine grain sizes, and the strain localizes in them. So if we see some passive markers that we can measure the displacement, there's roughly 1 order of magnitude higher strain rate within this zone than the bulk-induced strain rate. So the whole thickness of the shear zone would be around 0.6 millimeters, and the slip zones altogether, they are about 6 in the sample usually, measure 60 microns. So just the back of the envelope calculation, we can get 1 order of magnitude faster slip zones, faster strain rates within the slip zones. However, the velocity, the bulk displacement within this is always 10 to the minus 8 meters per second. And now to finally come to the steady state deformation, which is here at the end of the curve, then this would be the whole sample after the deformation. So we see the shear, this is about gamma 3.5 here. This would be the zone here that we deform. And here is an SEM image of the whole zone. And here we've been tracing the presence of the pseudotachylites. And we highlighted it in red, so we can see that this is a percolating layer that decorates those cracks that are actually these unloading cracks that happen at the end of the experiment, and that go from one side of the layer to the other. Those are just some examples of the microstructures that I'm going to talk much more in detail just in a second. So this layer here, again, just without the background picture, it's sometimes hard to exactly follow where it goes around these unloading cracks, so that's where we don't actually figure it out. But this is all the red material is just material where it's clear that there is some pseudotachylite, and this percolates from one side of the sample to the other side of the sample, and the topology of this melt layer might be described as a multiply connected layer, which is basically a layer that is interconnected, but there are still some holes where the material can touch in between, which is different than a simply connected layer, where we have just a material that is completely separated by some material in between, for example, the melt. So our topology is most likely a multiply connected layer. Now if we zoom into this area here, where this large amount of pseudotachylite can be observed, and we can see this is what it looks like. It develops along this C prime unloading crack, and if we zoom again into this area, then here we can see this through-going nature of the zone. Here it's fractured by this unloading crack, and we will focus now on the zone here that's B, that will be the next picture, and on this zone over here that's called A. So here we can already see that there's a biotite, which is high contrast in the backscatter image, and here it's mostly some feldspar material. And if we have a closer look, so this would be the picture A. We can see here the biotite, which is still crystalline, a sharply cut off quartz grain, and from this we have this very thin layer that's percolating, locally forms some tiny injection veins, and then it actually goes and opens into a much bigger region where we can see the clasts of quartz, some locally small bubbles here that have flowing textures. This would be the B example. Here we can see corroded clasts of predominantly quartz. We can see some clear bubbles that are following the local flow pattern. Those would be the black dots here. And those are, again, all features that are typically described for pseudotachylites. If we wouldn't know the conditions in which it formed, we would say that this is a pseudotachylite. I'll show some better ones. There's a really small one here. I'll go to the better injection veins later. Here again, this would be a clear-cut example of the melt itself. So here we can see this is the extremely fine-grained material. It's a 10 micron scale. And then it starts melting and forms these large bubbles. And you can see some locally, some higher Z contrast areas. And this all seems to me that it's quite clearly molten material that is derived from this extremely fine-grained material surrounding it. Now to some injection veins. So this would be again a layer that's sharply cutting through this quartz grain here. Those would be 5 microns, and within this layer we can observe like flow structures. These are almost Schlieren quartz grains, some amoeboid former biotides, and some smaller injection veins into the rock.
But there's no displacement here.
Well, there's a lot of displacement because you don't really see the surrounding the material, or you would need some passive marker. So if we have, for example, biotide that's entangled in the slip zone, then we can see quite well that the strain accommodated in those slip zones is much higher. So here it's a little bit hard to already find some passive marker that you could connect. This used to be here, this used to be there. There's obviously some flow structures, so there is some displacement. And for example, if I would go back to this example, then here is a sharply cut off quartz grain along this this very thin pseudotachylite. And on this scale, like the 5 microns, it's really hard to figure out where his counterpart actually is. So I believe there's quite some displacement on those zones. And here this would be another example. We can see here a biotide grain where we can still resolve that it's crystalline. And here on the part it starts melting, where we can see the formation of the bubbles, and again some quartz clasts that are swimming around this in this melt of biotide. Yes? The bubbles, they are so during the experiment they were most probably filled with a fluid, because if you melt a mica, then you release the water that is in the crystal structure, and it's very commonly observed in pseudotachylites. Another possibility how people explain it is that because they are moving very fast, and there's cavitation in this highly viscous layer. I'm not sure what the bubbles were really during the deformation, but after we take it, they are very indicative for this melt. I mean, the bubble must have formed either by cavitation or by the dehydration of the micas. They are voids, yeah, they are filled with epoxy now. Here would be another example of a very thin pseudotachylite, where we can see some quartz clasts swimming in this more whitish material. It seems, but it's hard to quantify, that the higher the strain rate, the thinner the pseudotachylites get. So this would be one from the 10 to the minus 3, where actually the fracture terminated the experiment. So this might have formed during the seismic event or before, as the other ones, where it's actually an extremely thin through-going layer that's on the order of 100 nanometers. So to finalize, there's some EDX maps of those things that we believe are pseudotachylites. And again, here we can see that this would be the melt layer. There are some quartz clasts that are surrounded by a quartz depleted material. It's enriched in iron and manganese. So they are those mica-derived pseudotachylites have typically a much lower Si content than the starting material. The bulk starting material is from an XRF. Those are EDX analysis. So there's 30% difference in the Si content, and 10% more iron than in the starting material, which is again something that's taken as an indicative for a disequilibrium melting for the production of pseudotachylites. This would be a feldspar-derived melt. Here we can again see this silica depletion, a slight iron enrichment, and we can see potassium, calcium, and sodium in better contrast on my screen. So we can see that, that we melt micas, we melt feldspars, we melt also quartz, and this is typically interpreted, because the pseudotachylites should form in the order of seconds, that it's the single phase melting actually is what matters. So if people observe molten quartz clasts, they infer temperatures on the order of 1700 degrees, which are the single point melting temperatures for quartz. So this would require an increase in temperature by 350 to 1400 degrees C in our experiments to be confined over hours. And I don't believe that this is a very possible assumption, and I rather think that the melting point depression of this extremely fine-grained nanomaterial amorphous zones might play a more important role. So there will be some increase in temperature based on the shear heating, based on the higher deformation of those zones. However, I doubt that we can reach temperatures of 1700 degrees in the experiment. And one last point to make is that this would be an again a deformed layer, and here this black part is the unloading crack that develops at the end of the experiment when we depressurize it. And if we have a look on the sliding surface, so if we would have a split sample, then we can take it and put it in the SEM and have a look on what actually looks like this surface that's open now. And here we can observe some striations in much more detail like this that are actually formed on the surface itself. So this would be a thing that's typically observed on fault surfaces, but it does not. It developed out of the thin volume that was deforming within the experiment, and then the unloading opened it up and revealed this surface. But the volume was the thing that was deforming and that was controlling the deformation behavior of this material. So to sum it up, we have at the end of compaction, we have the survivor grains with fragmented mantles that are very fine-grained. At the peak strength, we form slip zones that are around 20 micrometers thick, are partly amorphous with 10 to 50 nanometer big fragments. And during the steady state flow with no abrupt stress drop at 8 orders of magnitude slower than seismic slip rates, we observe those pseudotachylites that have corroded clast flow structures, bubbles, injection veins, more iron and manganese rich, and less silicic composition than the bulk rock, which are all arguments that are used to confirm the presence of a pseudotachylite. So to discuss, to come to the discussion, it's I would ask myself whether we really need an earthquake to make a pseudotachylite, because in our case they occur without stress drops at slip velocities that are up to 8 orders of magnitude slower than the slip velocities inferred from earthquakes. And I was wondering, I don't know entirely how this is calculated, but if the seismologists are speaking about meters per second of slip velocity, they already imply a zero volume deformation, right? Because if you have a seismogram, then you record the seismic waves, and then you use inverse modeling to figure out what was the source of this. And if you start with a slip velocity, then you already imply that there's a zero fault plane thickness that generates the earthquake. So I was wondering what is actually the strain rate during an earthquake, whether there is any data that people could figure out what is the volume that gets really deformed during an earthquake. I didn't find any satisfying answer to that, so I hope maybe some of you might know much better about this. Then melt lubrication, that's another model that's very often put through, which says that once we form this melt, once we form the pseudotachylites, the faults are expected to be extremely weak. But in our case, we observe steady state flow at shear stresses of 1400 MPa and a friction coefficient of 0.6. So obviously in our case, the formation of a melt layer does not weaken the fault. And we suspect that this is partly connected to the fact that this extreme weakening, this fault lubrication, is observed in the high velocity friction experiments only after a larger amount of displacement, when a through-going simply connected melt layer forms. In the beginning, before this through-going melt layer forms, they observe the formation of discontinuous patches, which is also connected to the increase in the friction coefficient. However, because we observe this forming on a quite a large scale, we don't expect that the melt layer would develop this this simple connected topography. So the last discussion point would be whether pseudotachylites are superheated, which in our case I believe is not the case because of the fact that our pseudotachylites don't form within seconds but take up to 12 hours in the slow experiments. Most probably this is there's a well-described phenomenon of melting point depression in the semiconductor industry. So to conclude, I would say that pseudotachylites cannot be used as an unequivocal evidence for seismic activity because they may form also in creeping segments of faults. I don't want to say that all the pseudotachylites that we observe are not connected to earthquake, but the fact that they might not necessarily be connected to earthquakes is, I think, worth studying. And this kind of follows that earthquake source parameters calculated from pseudotachylites have to be used with caution because many assumptions based in the calculations might be incorrect. Thank you very much for your attention.